Consider this, we have an 80% confidence level. If I change it to a 90% confidence level, let's see what happens to our margin of error, how far the black line goes on each side of the red in the mean in the middle. As I increase my confidence level, my margin of error gets bigger and bigger. And we go to a 90%, 99%, we have this compared to our 80%, which is this. So as your confidence level increases, so does your margin of error. And that's what we're trying to get to talking about this slide here. A higher confidence level is a higher margin of error. So you have a less precise estimate because you need to be wider to try to have a better chance of capturing the true mean. A lower confidence level means you have a smaller margin of error. So let's go ahead and take a look at these questions. Here we're trying to draw conclusions about our population mean from our sample. Now, what's not included? And what's not included here is our known value for our population mean. Now, the purpose of our confidence interval is to give us a range of reasonable values for the true population mean. Now, what's not included in our formula? And that is our population size. What do we hope to capture in our confidence interval? Our true population mean. In general, with all confidence intervals, it's our unknown parameter, which is a characteristic about a population. But for what we're going to be looking at, it's always our population mean. What are the three components of your confidence interval? You need an estimate of your population mean, your confidence level, and you need your margin of error. These are the three things you're going to need to evaluate the next several statements to see if they are correct confidence intervals or missing part of it. So let's take a look at this first one. We are 90% confident that the true mean is between this and this. Well, this would be an incorrect one because there's no statement of what we're trying to find the estimate of, as in no statement in words of what our true population mean is. Are we talking about weight of lambs? Are we talking about weight of people, weight of pigs, or weight of giant pumpkins? We don't know. So here, the average local or average time for local company for new insurance claims is 9 to 7 days. Well, this one is bad because there's no confidence level given. Are we 90% confident, 95% confident, or what? Here it says we are 95% confident that the mean of the sodium content in beef hot dogs is between this and this. In this case, it is a correct interpretation because you have your confidence level. You're talking about your mean of your population and describing what it is, and you're giving me your confidence range between here and here, or it could be given as an X bar plus or minus your margin of error, would not make a difference. So read through this, decide if this is a correct interpretation. In this case, it is not, because here it's saying the mean of the 100 students from the sample. And remember, your confidence level or intervals always need to be referring to the whole population. Consider this one. This one here is correct because you're given your 95% confidence level, you're given your confidence interval, and it's referring to the whole population. Now let's go ahead and consider the other main test of, or when we're looking at inferential statistics, we're going to look at the other main part, which is the test of significance. In other words, we're trying to see, is our mean from our sample truly all that different from the mean of our population? And if so, what evidence do we have to support that it is different? So the confidence intervals gives us a range of values we would expect. And this is going to give us a probability of how likely our sample is to be true to our mean, or our mean true to our sample. So here we have a situation where we have 4 packs of cherry tomatoes, which is a half a pound or 227 grams. The average weight ends up from our 4 boxes being 222. Obviously, we cannot expect each one of our um, samples to end up measuring exactly 227 grams for our population because we're dealing with whole tomatoes. Now, we're at 222, which is definitely smaller. But are we smaller by chance variation, or is the machine packaging the tomatoes need to be recalibrated? When we're looking at our test of significance, we are always going to try to test our hypotheses. We have 2 types of hypotheses. We have a null hypothesis and an alternative hypothesis. And a hypothesis is just an assumption or a theory that we have about our mean of our population. And we want to know, does our machine need to be calibrated, or, once again, is the variation of 222 grams just due to chance variation? The null hypothesis is always that there is no difference or there is no effect. The symbol for your null hypothesis is H with a subscript 0, often referred to as H naught. Your alternative hypothesis is what it is you're trying to find evidence for, which your alternative hypothesis is labeled as a capital H with a subscript A. Now, your hypotheses, your null hypothesis and your alternative hypothesis, always refer to your population mean. And since you're looking at your null hypothesis, meaning that there is no difference, you're always going to go your null hypothesis being your mean equaling whatever it is you were initially thinking your population mean was. Your alternative hypothesis is what it is you're trying to find evidence for. Are you thinking your alternative hypothesis should be that it's different, which you would want if you're trying to figure out if you need to recalibrate your machine, because if it's getting too big or too small, you'd want to know. So therefore, you'd want to know if it's different, meaning not equal. Now, there might be times where you have your null hypothesis being your mu greater than your number, or your mu being less than your number, depending upon the situation. But once again, your null hypotheses and your alternative hypotheses always refer to the mean of your population. Now, just as what we were talking about a little bit ago, your alternative hypothesis could be a 2-sided where it's not equal to a number, or it could be 1-sided where it's less than a number or greater than a number. But once again, your null hypothesis is always your mean equaling a certain number. It's always an equals there. Now, whether it's a greater than, a less than, or greater than, less than, or not equal to is all in the context of the problem that you're looking at. So suppose we have this one here, where we're looking at a generic drug and the absorption of that drug compared to your name brand. If it's higher or lower, we could have a problem. So therefore, we would have a not equal to for our alternative, because we'd want to know if it's significantly different one way or the other. So how do we choose? Once again, it's all in the context of the problem, and we always make a choice prior to going ahead and doing our test. So here, a health advocate group tests whether the mean of the nicotine content of a brand of cigarettes is greater than the advertised value of 1.44. Since it says sorry about that. Since it says greater than, your alternative hypothesis is going to be mu greater than 1.4. Once again, your null hypothesis is always going to be mu equaling whatever number it is you have. Now, the test for the mean is using your z-score again. Now, we're looking at our samples, so that's why we have over the square root of n down here rather than just our sigma. It needs, for our test, we need to know our standard deviation. It needs to be normally distributed. And we don't know the population mean. Now we're going to end up with a p-value. That's the area underneath of our curve. In chapter 3, the area underneath our curve was our probability. And that's what we're going to be finding here, is the area underneath our curve, either less than a particular value, or in some cases over here, greater than a particular value. And that's what we did in chapter 3. That area underneath the curve here we're going to refer to as our p-value. Now, your x bar minus your mean is also referred to as your observed effect. So, let's go back to our tomato problem. When we go ahead and carry out our test of significance that we have with our z-score formula here, on this, we're going to end up finding an area underneath our standard normal curve. That'll be our p-value. Basically, it's going to let us know what are the chances of us getting a 222 gram average from a sample of 4 if this was just chance variation. It tells us how believable this is. Now, if you have a small p-value, you then end up knowing that it's not likely to occur by chance alone, and that something else must be occurring. But how do we figure out that p-value? Well, if your null hypothesis is greater than, that means when you're looking at your standard normal curve, you're going to be looking at that score and the area that's above that. If your null hypothesis is less than, you're going to be looking at that z-score and what the area is below that. And remember, your standard normal curve always tells you what's below. Now, if you're dealing with a not equal to, that means you're wondering what's below that particular value, and then what's above that other z-score on the other end. Basically, you find out what's below your first value, and since both of these ends are the same, you take and double this one value here for your p-value. However, we are typically not going to be calculating this by hand, so we don't normally have to remember to go ahead and double this, because the technology will do that for us. So once again, that p-value tells us the chance that if it was just done by random variation of how believable we are with that answer that we got. So a small p-value tells us that it's not likely to occur by chance alone, that something must be influencing our information. So if we have a small p-value, we want to reject your null hypothesis. And if we reject your null hypothesis, we would say it's statistically significant. So thus, a small p-value is strong evidence against your null hypothesis, but how small? So here are some examples of different p-values. A two-sided of almost 27%, a one-sided of 17%, but almost 9% two-sided. So how small do we want? Well, typically we want to be at a 0.05, 5% or smaller. Now, 5% is not necessarily a hard cutoff number, but it's typically used.